Hey, what's up, guys? Yeah, so today, let's talk about a distinguished open set. Yeah, sorry, I just spelled it wrong. Distinguished open set in the affine scheme. So basically, I just define a V of F, right, to be the priorities of in a spectrum of X, A, such that the P, F contains P. And then one can, as I say, V of F is closed, right? So this tells you that D of F, if I define D of F to be X minus V of F, basically it's all prime ideals which do not contain F. Okay, so obvious that this guy will be open. Okay, so everything that everything in the sheaf that we will say will define OX sheaf, the structure sheaf on a D of F to be just AF, where it's a ring, where this is the ring localization. Basically, it's A divided by F to N, where A belongs to A. Okay, and in the future that I will show that one can actually prove that this guy is indeed a ring. Okay, sorry, is indeed a sheaf ring. So this guy is not non-trivial, but a sheaf ring. And if you you can also define yeah, okay, so this is maybe we see in the future. And you can also show that this will give you the stocks, right? If you start from some stocks, you have the distinguished open set, and then you define a ring, and then you can prove the stock is just AP. Okay, AP is the localization of prime ideals. Basically, it's A minus P inverse localized at A. And I will also show that I will also prove this link. Okay, but in this video that I just basically want to show some property of distinguished open set and tell you that why the distinguished open set will form the basis. Oh, by the way, and I will also provide a video that show this AP is actually the local ring. Okay, so you can check out my other videos. This guy is a local ring. Okay, so local ring means that there is only one maximum ideal. Okay, so now let's talk about the property of the distinguished open set. And you can also check the Veckel 3.5. Basically, I think these are basically some exercise of the Veckel, but basically I give the proof. Okay, so first one is that F of and G, if F of G belongs to A, the ring then D of F intersection of D of G will be D of FG. And this is very simple. So I think you guys can let's quickly prove it. And obviously that so this is the prime ideal do not contain F, right? So let's prove this. Okay, so this is if F do not belongs to P, and the G, maybe this is a bad notation. Let's say there's an element called alpha belongs to this and belongs to this. So this means that F do not belongs to alpha, and the G do not belongs to alpha, where it is a prime ideal, right? Remember, alpha is a prime ideal, so it's obviously that we will have FG do not belongs to alpha, right? Otherwise that either one of it will belongs to alpha because alpha is a prime ideal. So this is trivial. And the second direction is, so this direction is trivial, right? Because that alpha do not belongs to, right? So, okay. Now you can also prove this. Basically, it's the same, right? If there is a prime ideal belongs to this, then which tells you that F or G do not belong to alpha, then by property of prime ideals, that F should not belong to alpha and G should not belong to alpha. Otherwise, that one of it belongs to alpha, they will reverse these results, right? So trivial, right? Okay, and another property is that also most importantly used is that D of F, and that if they are the same, then if only if square root of F, square root of the radical of the ideal generated by F is the same as radical ideal generated by G. And this is just basically there is a mysterious formula that I will prove in our videos that radical of S is all the prime ideals belongs to V of S intersection with P. Okay, so if you have this, then obviously that this tell you that all the prime ideals do not contain F, and all the prime ideals do not contain the G is the same. But basically, this tell you that this basically tell you what? This basically tell you that V of F singleton is basically the same as V of G singleton, right? Because all the prime ideals do not contain F. It's the same as all the prime ideals do not contain the G. But basically, this tells you that all the prime ideal contains F is the same as all the prime ideals contains the G as a set. So we say as a set. And obviously, that if you plug this formula, that you prove these results, right? Because you plug this formula to this, then this tells you that if you take all the prime ideals contains to V of the singleton of F, P prime ideal will the same as all the prime ideals contain the singleton of G and the prime ideals. Then these two will give you the square root of F, radical of F, and radical of G. Okay, so now basically we just prove this direction. Okay, but obviously, right? Obviously, if you have this, right? Basically, you are just saying that the P, the prime ideals do contains the V of this singleton of F. P belongs to this V, the vanishing set of singleton of F. Is the same as the P belongs to this, right? But this is exactly the same as just saying the. So basically, you are saying that all the prime ideals contains F. It's the same as all the prime. It's all the prime ideal in the vanishing set of F and all the prime ideal in the vanishing set of G. Their intersection are exactly the same. Okay, but this is the same as you are saying that the prime ideals do not contain F. It's the prime ideals do not contain G. They are the same set. Okay, so basically this is the will implies this. Okay, so basically these are somehow like the just the restatement of this formula. Okay, so the previous formula is non-trivial, so I will prove in the next videos. Okay, so now so what I'm going to tell you is that D of F will actually forms a basis. So you take all the F in A and then you basically take this D of F will forms a basis. Forms a basis. Okay, so it's open. So forms a basis means that you need to prove that any open set is the union of its D of F. And this is very simple. If you take open set of, so T of X means the open set of the spectrum. And obviously that you can write X to be minus delete some V of S, right? So this guy's closed. Okay, but this is what? This is just saying that so remember your V of S is a prime ideal, do not containing S, right? So it's the prime ideal containing S. But this is the same as the prime ideal contain each element in S. So basically it's the V of F. Okay, because all the prime ideals which containing F, right? And then you do the intersection. So this so your simple set theory will give you the U equals to X minus, is a union of X minus V of F for each F belongs to S. Basically union of F belongs to S and the D of F. Okay, so any open set is the union of distinguished open set, which proves that the distinguished open set forms the basis. Okay, and another property is that this D of another property is the following, which for all F belongs to A, D of F is quasi-compact. This is almost the same as right in the algebraic geometry that I think quasi-compact is the same as compact. Okay, so basically it's like all the open cover of D of F will have the finite subcover. This is the same as the covering space, right? I mean, the standard, like at the standard definition of compact. Okay, so basically the goal is to show that let's say if D of F is the union of distinguished open set, because we usually we need to show it for open set. It's for all the open covering, right? But we already proved that D of Fi is a D of Fi is already forms a basis, so we only take this form, and then we want to show that this guy is a finite subcover. So let's take J to be the ideal generated by I. Let's say this is the index I. Okay, so I take J to be ideal generated by this. Okay, so which tell you that the vanishing of F by definition is covers basically is covers V of J. Okay, so this is the previous property of vanishing set, and this tell you that use the previous results, right? Previous results that we know that the radical of J will cover the radical of F. Okay, by previous results. So this is basically the restatement. This sentence is a restatement of this sentence. Okay, you can check by yourself. Because the subset of V of J, if you do all the intersection, you get this. Okay, you do all intersection. Okay, but this tells you that F of n belongs to J. Right, by definition, or some n equals 0. Okay, so this tells you that F of n will belongs to this element, right? So F of n will be some will be J, will be some element J, right? So F of n will be the linear combination of some finite element in J. Okay, so F of n will belongs to a subideal J prime. Okay. Okay, so we know that F of n is a subideal J prime. It basically belongs to subideal J prime, where generated by finite element because F of n belongs to J, right? So you can find a linear combination of element in J such that F of n is the same as this guy. So F of n belongs to subideal J prime. Okay. So this basically say that V of F, right? Note there the important formula that I didn't show is that V of F is the same as V of Fn, right? Because there are only considered prime ideals. It's a subset of Vj prime, right? Because I know that is right. Okay. Okay. So and I also know that V of J prime is a subset, right? Okay. So let's write this. Let's write J prime to be the I belongs to I prime. So I prime is finite. I prime is a finite, which is the F of n belongs to linear combination. So V of J prime. This is the same as so V of J prime is the linear, is the ideal generated by this. So it's the intersection of all the Fi. Okay, so this tell you that the distinguished open set because V of F cover this. So if you reverse, you prove that distinguished open set is union of B of Fi I prime, which is finite. Okay, so corollary, the spec of A of D of 1 is quasi compact. Okay, so now yeah, I think this is good, and yeah, that's it. So maybe next time we say another we talk about the irreducible and the integral domain.